In this lesson, we're looking at similarity in right triangles. So the Explore activity has us making 2 copies of the same right triangle on a piece of paper and cutting them out, which I've already done. And then take one of the triangles and fold it to find the altitude to the hypotenuse. So what they want us to do is fold it along this line so that the side is coinciding with itself until I'm going through this vertex. So I'm folding, 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 and it's about here. So then it says cut the second triangle along that altitude. Okay. And label the triangles as shown. So this is triangle 2, this is triangle 3, and this is triangle 1. Okay, what now? Place triangle 2 on top of triangle 1. What do we notice about the angles? Well, notice that the right angles are congruent. This angle I could line up with that one, and this angle lines up with that one. So what do I notice about the angles? The angles are congruent. What is true of triangles 1 and 2? Well, if the angles are congruent, then triangle 1 is similar to triangle 2 by angle-angle similarity. And repeat that for triangle 1 and 3. So notice that those angles line up. Similarly, these angles line up. And these right angles line up. Yes. So how are the hypotenuses of triangles 2 and 3 related to triangle 1? Okay, so hypotenuses of triangles 2 and 3, and what is their relationship to triangle 1? Well, the hypotenuse of triangle 2 is this leg of triangle 1. And hypotenuse of triangle 3 is the other leg. So hypotenuses of triangle 2 and triangle 3 are legs of triangle 1. And what is the relationship between triangles 2 and 3? Well, if triangle 1 is similar to triangle 2 and angle 1 is also similar to triangle 3, I could say by transitive property that triangles 2 and 3 are also similar. When you draw the altitude to the hypotenuse of a right triangle, what kinds of figures are produced? Right triangles that are similar to the original triangle. Suppose we draw triangle ABC such that B is the right angle and the altitude to the hypotenuse intersects hypotenuse AC at point B. So let's draw that. A, B, C, and the altitude to the hypotenuse would be about there. Match each triangle to a similar triangle. Okay, so A, B, C would be similar to triangle, well, none of these start with A, so what I'm looking for is an angle that is congruent to angle A in a smaller triangle, so maybe this triangle here. So angle B would correspond to angle A, So that's this one. Angle or triangle PBC. Well, P is my right angle, so if I'm talking about triangle PBC being similar to another triangle, it better start with a right angle. So C is not a right angle, so kind of by default, it must be similar to triangle PAB. And then triangle BAP is similar to triangle CAB. Using corresponding parts of similar figures is how I identified which. So a little bit of vocabulary here that's going to relate to the diagrams that we've been talking about. If I have a proportion like this, where two of the numbers in the proportion are the same and they're being multiplied by each other when I cross multiply, then I would say that x is the geometric mean of a and b. So when I cross multiply this, I get x squared is equal to ab, and then I would take the square root of both sides of the equation and find that x is the square root of the product, ab. And so in example 1, they have us finding the geometric mean of two numbers. Finding the geometric mean of 4 and 25, set up the proportion, and then they are cross-multiplying and solving. Similarly, we're going to set up 9 over x equal to x over 20. They have us multiplying both sides by the product of the denominators. Okay, so the two denominators are 20x, so they have us multiplying by 20x. You know what? I'm not terribly fond of this, and I think it's going to confuse some of you more than help some of you. I think most of you are pretty comfortable with cross-multiplying. X times x is this x squared. 9 times 20 is 180. So when I take the square root of both sides, I have the square root of 180. And so we're simplifying that radical, and we've talked about that. Now I want to simplify this radical. And what I mean by that is I want to remove any perfect square factors from 180. So let's talk about what 180 is divisible by. Let's also talk about what perfect squares are. Perfect squares are numbers like 4, 9, 16, 25, 36. And they're perfect squares because 4 equals 2 squared, 9 equals 3 squared, 16 equals 4 squared, 5 squared, 6. 180, I hope you would notice, is divisible by 9. And 180 divided by 9 is 20. Oh, well, that's pretty interesting because 20 is also divisible by 4 and 5. So what that means is that the square root of 180 is equivalent to the square root of 9 times the square root of 4 times the square root of 5. Well, hopefully you know that the square root of 9 is 3 and that the square root of 4 is 2. So that's 3 times 2 times the square root of 5. So that's 6 radical 5. So we've simplified radical 180. It is equivalent to 6 radical 5. And you did learn this in algebra last year, or at least you should have. So how can we show that if positive numbers a and b are such that a over x equals x over b, then x equals the square root of ab? By cross-multiplying. So let's find the geometric mean of a few more pairs of. So we set up the proportion, 6 over x equal to x over 24. X squared will equal 6 times 24. So I pull out my handy dandy calculator, and 6 times 24 is 144, and that's pretty convenient because when I go to take the square root of both sides, x is 12. Number 7, we start by setting up the proportion. 5 over x equals x over 12. Cross multiply, we have x squared equals 60. Take the square root of both sides, and x is the square root of 60. But you are expected to simplify this radical. You are expected to ask yourself, is 60 divisible by a perfect square? It's divisible by 4. So that means we can rewrite the square root of 60 as square root of 4 times square root of 15. Is 15 divisible by any perfect squares? No. So square root of 4 is 2, so we get 2 radical 15. So coming back to the geometry now, we discovered a theorem about right triangles and similarity. And actually we kind of discovered 2 theorems, and you see them here. That the altitude to the hypotenuse is the geometric mean of the 2 lengths of the 2 segments of the hypotenuse, and that each leg is a geometric mean of the hypotenuse and the segment of the hypotenuse adjacent to the leg. Okay, so I label the triangle sometimes a little bit different than the way they labeled it. So let me share that with you. I label this as the hypotenuse. This is my altitude to the hypotenuse. Hypotenuse is now broken into 2 segments, segment 1 and segment 2. And each one of those segments is adjacent to a leg. We'll call them leg 1 and leg 2. And that means that these proportions boil down to this one I can consider as segment 1 over A equals A over segment 2. And I've come up with a mnemonic device to help you remember this. Some apples are sour. Maybe that'll help you memorize that proportion. And then this boils down to S over L equals L over H. And what I use, hopefully that will help you remember this proportion, snarling linebackers, if I could spell, like hitting. So maybe that'll help you remember these. But first, we're going to prove them. All right, so I have triangle ABC with altitude BD, and I know that the triangles are similar by angle-angle theorem. And so CD, first and third, over BD, first and third, equals BD, second and third, over AD, second and third. That's corresponding parts of similar figures are proportional. And the proof of the second geometric means theorem would follow pretty much the exact same lines. You've got the triangle with the altitude. That means you have 2 similar triangles, and that means you have corresponding parts that are proportional. So let's use these proportions. In example 3, part A, we're finding the value of x. X is an altitude, so it's going to be the geometric mean of the 2 segments of the hypotenuse. So they set up the proportion, and they didn't really cross multiply, but you end up here, and then they simplified. In order to solve for y, I realized that y is a leg, and it is therefore the geometric mean, so it goes in these two spots, of the whole hypotenuse, which is 12, and the segment of the hypotenuse adjacent to y, so the part of the hypotenuse that's touching y. And so I'm going to skip this because it's just weird, and I'm just going to cross multiply. Y times y is y squared. 10 times 12 is 120. Take the square root of both sides, and I get that y equals the square root of 120. All right, so square root of 120. I need to break that down. Where's that list of perfect squares? Okay, so I look at this 120, and of course this goes on, you know, it's 49 and 64 and so on and so forth. But right away, I hope that you'd notice 120 is divisible by 4. All right, so let's check that out. Square root of 4 times, well, 120 divided by 4 is 30. Okay, is 30 divisible by any of these numbers? No, it's not. All right, so this is approaching as simplified as it's going to get. The square root of 4 is 2, so I have 2 radical 30. How can we check our answers? Well, if I just found out what x was here, and I found out what y was, notice this right triangle. When I have a right triangle, remember we can use Pythagorean's theorem. So we could take those side lengths and plug them into Pythagorean's theorem and verify that a squared plus b squared equals c squared. So in this your turn, we're on our own. Let's solve for x first. Since x is an altitude, it is the geometric mean of the two segments of the hypotenuse. So 5 over x equals x over 7. Cross multiply and solve. I have x squared equals 35. I take the square root of both sides, and 35 isn't divisible by any of these numbers. So x is just square root of 35. Now let's figure out y. Y is a leg. That means it is the geometric mean of the whole hypotenuse, which is 12, and the part of the hypotenuse that's touching it, which is 5. So I have y squared equals 60. Take the square root of both sides, and we simplified this earlier. We simplified the square root of 60 here. So we're going to get the same answer. Y is 2 radical 15. And we've used Pythagorean's theorem here and there throughout the course. Now we're proving it. So I have this right triangle. I'm trying to prove that a squared plus b squared equals c squared, and I'm going to use that altitude to the hypotenuse. All right, so I know that angle BXC is going to be congruent to angle BCA because all right angles are congruent. Angle B is congruent to angle B by reflexive property. So triangle BXC is similar to triangle BCA by angle-angle similarity. Angle AXC is congruent to angle ACB because all right angles are congruent. Angle A is congruent to angle A, also by reflexive property. And so those triangles, AXC and ACB, are similar by angle-angle similarity. In this first proportion that they're wanting me to fill in the blank, they have A over C. Well, what's A? It's BC. And what's C? It's BA. So they've got first and third over first and third. That makes sense. Equal to something over BA, over segment A, which is BC in this triangle. Well, that's first and second. So what corresponds to that? That's BC over here. What's BX, and that's E. Similarly, in the second proportion, they've got B, which is AC, over C, which is AB. So that's first and third over first and third. That makes sense. Equal to something over B. Well, B is AC, so that must correspond to AX, which is D. And now they say, perform some algebra to complete the proof as follows. Multiply both sides of proportion 1 by AC. So once again, what they've got us doing here is the same kind of weird math that they had going on here. I don't understand why they're trying to make cross-multiplying more difficult than it needs to be. Let's just cross-multiply. We end up with a squared equals CE. And when I cross multiply, okay, so I got this by taking this proportion and cross multiplying. My second equation here is going to be what I get when I cross multiply these. So that's B squared equals CD. Add the two resulting equations and I will get A squared plus B squared equals CE plus CD. And then it says factor the right side of the equation. So what they mean is they want us to notice these two terms have a greatest common factor. It's C. And when I factor C out, what I'm basically doing is undistributing. Well, what do I do when I distribute? I multiply. So when I'm factoring, I'm dividing. So CE divided by C is E, plus CD divided by C is D. And I'm going to use the fact that E plus D equals, well, let's look at the diagram again. E plus D equals C by segment addition. And I'm going to rewrite the equation as A squared plus B squared equals C squared. A student used the figure in part 2 and wrote the following incorrect proof. So let's see what they did wrong. They used that CX was F, and they have E over F so this makes sense, and then they cross-multiplied, and since the triangles are similar, they are right triangles, and that means A squared equals E squared plus F squared, and B squared equals F squared plus D squared. Well, now hold on a second. There's where the error in the proof is. And it's not so much that they're saying something that's incorrect, it's that they're trying to prove the Pythagorean's theorem. You can't use the Pythagorean's theorem to prove it. Okay, so this is circular reasoning. The student used Pythagorean's theorem to prove Pythagorean's theorem.